Hello students, welcome back. In today's class, I am starting a new chapter, that is Junction Diode. This is chapter 32. This chapter is from semiconductor devices. The first chapter was semiconductor itself, and this one is junction diode. So in this chapter we are going to study about diodes made up of semiconductor. The first topic is PN junction diode. Now in the previous chapter we have studied about there are two types of semiconductor, p-type and n-type. So when p-type semiconductor and n-type semiconductor are combined together in such a way, this becomes a PN junction diode. So a PN junction diode is a two-terminal device. It is also known as solid state diode. Now we know that p side has, this is a semiconductor, so majority of charge over here, charge carrier or majority charge carrier is hole. So hole is positively charged, so majority charge carrier over here is positive, that is hole. Now in the n-type semiconductor, majority charge carrier is electron, which is negative. So p side is mostly positive and n side is negative. Now when they are combined together in such a way, this becomes a PN junction diode. Now what happens when this is connected to external source? So first is forward biasing. Biasing means to connect this PN junction with external source of energy. So we have P and N type semiconductor combined together. Now forward biasing means P side, which is already positive, it is connected to positive terminal, and N side, which is negative, connected to negative terminal. So this is external source where positive P side is connected to positive and N side is connected to negative. Now when positive terminal is connected to the P side of the junction diode, what happens? A large current flows. So first is large current will flow through it, and this arrangement is known as forward biasing. Okay, this type of combination is forward biasing. Now reverse biasing, we'll study this, what is happening, this everything in detail. Just now I'm just giving you the diagram. Okay, now in the reverse biasing, is when P and N type is connected to external source but with opposite type of energy source. P, which is positive, connected to negative, N, which is negative, connected to positive. This arrangement is known as reverse biasing. In this one, what happens is small current flows. Okay, this is the basic idea. Now a diode offers very little resistance to the flow of current under forward biasing, and it offers extremely large resistance in the reverse biasing. So in the forward biasing, resistance is low. In reverse biasing, resistance is high. So to remember this is the basic idea of forward and reverse biasing. Now the symbol for a diode. Symbol in an electric circuit, we know that symbol is very important. So symbol for a PN junction diode is like this, arrow kind of thing and with a line. So this is a diode. This side represents negative side, which is N side. This side represents positive side, which is a P side. So if you draw a diode, this side is positive, this side is negative, this side is P, this side is N. So we need to know and this diagram because we will use this type of symbol many times when we draw electronic circuits. Okay, this is it. Now we'll talk about charge depleted layer. So another topic is, in your book, all these topics are combined in the same topic, that is PN junction diode, but I am breaking the topics so that will be easier for you to understand. So now we'll study about charge depleted layer. Now we know that P side has a larger concentration of positive charge and N side has a lesser concentration of positive charge. So let us consider this box. Okay, let us consider this side, this box, to be P, and this box over here, I'm just drawing a magnified diagram so to show you what is happening inside. Okay, so now P side has higher concentration of hole, and N side has higher concentration of electron. So this P side has higher concentration of hole, this N side has higher concentration of electron. Now when we combine the both, diffusion takes place. So when we combine P and N, diffusion of hole and hole which is present over here, electron which is present over here, that takes place. So hole diffuses from P to N. So hole which is over here will move from P to N. So I'll just write it over here. Hole diffusion takes place in this particular direction. And electron diffusion, because higher concentration of electron is present over here, so electron diffusion takes place from N to P. So hole which is positively charged moves from this side to this side, electron from this side moves towards that side. Now next, when electron diffuses, it leaves behind positive charge. So when electron from this side moves towards P side, okay, then it leaves behind positive charge, positive immobile charge. So this positive space which is created over here in the N side is because the electron from this side has moved towards P side. Okay, it leaves space over here, that is positive space charge region. So this space is known as positive space charge region. Similarly, when hole diffuses, it leaves behind negative charge. Hole from P side moves to N side. So when hole is positively charged, so when positive charge moves from P to N, it leaves behind negative charge, negative space region. Okay, not charge, negative space charge region. These all are negative. So this side is known as negative space charge region. So what is happening over here? Electron from this side, the excess of electron moves towards P side, hole from P side moves towards N side, and there will be this type of region created. This is positive space charge region, which is immobile. Immobile means which cannot move, which is like this only. And over here is a negative space charge region which cannot move towards this side. So this region combinedly, this region is known as depleted region or depleted layer, known as depletion region also. So this is immobile charge which cannot conduct current and is depleted by conducting electricity. Okay, this cannot conduct any current. This is just a region. The property of depletion region is, first one, you can note it down, space charge region on either side of the junction. So this is a space charge region. Diffusion of majority charge carrier gives rise to depletion region. This majority of charge being diffused to either side creates this sort of region. Depletion region gives rise to drift of minority charge carrier. Now, what happens next is, after this doesn't stop over here. What happens next is, in the area of depletion layer, in this area of depletion region, electric field will rise because there is negative and positive charge over here. So what happens when there is negative and positive charge? Electric field will arise, and because of the electric field there will be a drift of minority charge carriers. So over here electric field will be there, so electric field will be induced, and because of the electric field minority charge carrier will start moving. So in the n side, what is minority charge? In the n side, minority is hole. Okay, in the p side, minority is electron. P is positively charged region which has got electron as minority. N is negatively charged region which has got minority as hole. So now minority charge carrier will start getting drift. So electric field region will be there. Electric field directs from positive to negative. So this is the direction of electric field. Okay, electric field direction. Now because of this electric field, what happens? Drift will be there. So hole, which is minority over here, will start getting drift to this side. So this is hole drift. Electron, which is present in the minority over here, will start moving this side. So this is electron drift. So electron will move towards n side, hole will move towards p side. So what is happening is, first of all, in the first step it is diffusion. Diffusion of hole from p to n, electron from n to p. From diffusion, what happens is depletion region will be created. Depletion region will be created. Because of this depletion region, electric field will be generated. And because of the electric field, there will be drift of minority. Okay, diffusion is of majority carriers. Drift will be of minority carriers. As diffusion increases, depletion region will also increase. So this region will keep on increasing, and electric field will also rise, which gives rise to higher hole and electron drift. So as diffusion increases, depletion region increases, electric field will also increase, which gives rise to drift. So initially, I write in the next page. Initially, now whenever electron moves, it creates current. Okay, whenever electron moves. So initially diffusion is there. So diffusion current is created. Diffusion current is large and drift is small. Later on, what happens? Just the opposite. That is, diffusion will be equal to drift current. So when diffusion current and drift current becomes equal, PN junction is under equilibrium. So this is equilibrium condition. Drift and diffusion becomes equal. Now next term is when p-n junction is under equilibrium, if diffusion and drift is equal, what happens? No more motion of electron will be there. So current becomes 0. This is under this equilibrium condition. So potential difference between n and p will also be there. Or potential difference of p and n is also known as barrier potential. Barrier means which stops the motion of electron. That is why it is known as barrier potential, denoted by Vp. So the definition you can write down. Potential difference is developed between n region and p region, which restricts flow of majority charge carriers across the junction. It is also known as barrier height. So when at this condition electron stops moving, current becomes 0. A potential will be rise, that is known as barrier potential, or also known as barrier height, where no more electron moves forward. Okay. Now we'll study in depth about operation under forward bias after understanding the depletion region. Okay, now over here, this is the connection of forward biasing. Forward biasing, P is connected to positive side, N to the negative side. So now, what happens when this is connected to external source? Suppose this is V. When external voltage V is applied, the holes in the P side will get repelled. Okay, what happens when positive and positive is connected? Positive repels each other. So this P is repelled and it will move towards, this hole will move towards N side because it is being repelled by the positive side, positive terminal over here. Positive gets repelled, so it moves towards this side, towards N side. Similarly, when negative terminal is connected to N, the electron over here gets repelled and it will move towards P side. Now the depletion width will, what happens when it moves from one to other side? There is a depletion width, a depletion layer region over here. If hole is moving this side and electron is moving this side, this depletion region will become small. It will be reduced. And when the depletion region is becomes small, the barrier potential, which is over here, will also reduced with depletion width. So barrier potential WB decreases with the depletion region. Okay, I will tell you again. When positive is connected, holes will get repelled, it will move towards N side. Similarly, N side, and when this negative terminal is connected, electron will get repelled and it will move towards P side. So when this move towards the opposite side, the depletion region over here will get smaller. And when this gets smaller, it will be easier for electron to jump from one side to another side. So the potential barrier or the potential barrier height decreases with the depletion region. Due to the decrease in the height of barrier potential and reduction in the width of the charge depleted region or this depletion layer, the current due to diffusion increases drastically. So when hole moves this side, electron this side, there is diffusion current that increases drastically. As an external voltage, if this external voltage will increase, flow of current will also increase. So if this increases, current also increases. As soon as the applied voltage exceeds the barrier voltage, if this VB becomes greater than barrier voltage, okay, the barrier voltage, then the barrier disappears. This barrier over here disappears and a large current flows through the diode. So under this condition, when external voltage becomes greater than the barrier voltage, then this barrier over here will disappear and a large current will start flowing under forward biasing. Now over here we'll study about the characteristic of forward or PN junction under forward biasing. Now this is the circuit diagram for forward biasing. Over here we are using ammeter and voltmeter to measure the current and voltage or potential difference, a resistance or rheostat, and external power supply. So this is a rheostat, this is a external voltage supply, okay, external voltage supply. This is ammeter and this is voltmeter. A small resistance is also developed due to the circuit. Okay, due to the circuit, a small resistance will also be developed. Now this is in forward biasing, as positive P side is connected to positive, N side connected to negative. Now the current in the forward bias junction increases rapidly with the applied voltage. As soon as we connect it, we close the circuit, the current starts flowing. Okay, this is also connected. Okay, the current starts flowing and the current will rise. Hardly any current flows in the beginning. In the beginning, current will be less. Slowly, as the junction barrier is decreased, current will start increasing. Now when the external voltage becomes greater than the potential barrier, the current increases rapidly. This I have already told you, increases rapidly. Now this barrier voltage, for silicon it is 0.7 volt, for germanium it is 0.3 volt. So initially the current is less. As soon as the external voltage exceeds this value, the current in the circuit increases drastically. So if you draw a graph for this one, this side is current, this side is potential difference. So if you draw a graph for example for germanium, it will keep on increasing in a slower, steady manner. But after a certain point, what happens? This is 0.3. After 0.3, the voltage will increase drastically. Okay, this is the sort of graph for forward biasing type of a circuit. Okay. Next, we'll discuss about operation under reverse biasing. In reverse biasing, P side, which is positive, is connected to negative side, and N side, which is negative, connected to positive side. Now when external voltage, this is V, external voltage is applied, barrier height becomes, over here the barrier height will not decrease, but in reverse biasing the barrier height will increase with this factor. Now depletion region width increases. Okay, depletion region, this depletion region will also increases. Why is that so? Because if positive and negative is connected, it will get attracted, so the hole will move towards this side. Over here, if negative and positive is connected, electron will move towards this side. So when the electron and hole move in the opposite direction, this width, this barrier width will increase, this width will increase. So more amount of negative space region will be created this side, the more amount of positive space region will be created over this side. So as the voltage is increased, more space region or this width will keep on increasing, and due to this, electric field will be generated from positive to negative side. Okay. Now because of this width, what happens is, because of this depletion region, what happens? Flow of electron from N to P side. Now because of this width, electric field is developed. Due to electric field, what happens? There will be drift of minority charge. So N, in the N, minority is electron, so electron will move from N to P side. Okay, due to electric field, drift will be there, drift of minority in the n side. Okay, in the n side, what happens? Electron will move from n to p. Now in the p side, holes will move from p to n. This is the drift, okay? But the majority charge carriers will be less. The diffusion current will be very, very less. Since the width is increasing, the electric field strength increases. As a result, the drift occurs. Okay, this drift is due to the electric field strength, but the diffusion is not there. Diffusion is very, very less. It's suppressed because diffusion means the motion of holes, majority charge carriers from P to N. Majority is P, but it is not moving from P to N. It is moving from P to this battery. Okay, so it is moving in the opposite direction. Instead, what is happening? Drift of minority carrier is happening due to the electric field generated by this space charge region. So under reverse biasing, no majority carriers flows across the junction. This majority carriers will not flow across the junction. Minority carrier drift occurs across the junction. Because of the electric field, minority will be there moving. So total current over here, total current is due to the hole drift plus electron drift. Okay. Now with this drift, what happens is, if this keeps on moving in this direction, what happens? In the reverse voltage, if this reverse voltage is kept on increasing, then what happens is, point is reached when the junction insulation breaks. This junction insulation will break at a point, because if you keep on increasing this voltage, and the reverse current rises sharply. So this current rises sharply if this gap keeps on increasing, and that is known as junction breakdown. Okay, due to this, what happens? There will be junction breakdown. There are two types of junction breakdown: avalanche breakdown and Yojana breakdown. We don't have to go this in detail. So now we'll learn about the characteristic of the reverse biasing. So for that, I'll just draw a small diagram. Reverse biasing means when the diode is connected, current is very less, so we'll use a microammeter. This is connected to a voltmeter, and then again to a rheostat, then the external source. So P side is connected to negative side and N side towards the positive side. This is the circuit diagram for reverse biasing. So according to this, what happens is, when it is in reverse biasing, a very small current will be flowing initially. Small current will be developed. The reverse current reaches saturation value as the external source is increased. The current is also known as reverse saturation current. So what happens if I draw a graph for this situation? If I draw a graph of reverse current, then this side is current, this side is voltage. Now reverse saturation current will be very, very less initially. Okay, it's very, very less initially, and it will reach a point when the current will be saturated. So at a certain point, the current will be saturated. It's also known as saturation current. Okay, saturation current. And at a certain point, when you keep on increasing this voltage, this current will drastically increase, because when the insulation, when we keep on increasing this voltage, the insulation breaks, and what happens at that point, randomly the electron will move towards p side. So it can have a random motion because there will be no more barrier, and the current will increase drastically. So at that point, what happens, the current will increase drastically like this. So this will be a diagram. So this point is a breakdown point or junction breakdown. This point is known as a junction breakdown. So this will be a graph for a reverse biasing. Okay, so this much for today. We'll continue in the next class.